So for the final part of this analysis, we're just going to examine the pressure distribution through the capillary tube for the various cases. So we're starting here on the formalism of Jern's law, and we'll proceed to the next slide, which is going to start looking at that pressure distribution. So here we're looking at the case where theta is less than 90 degrees, for example, water in a capillary tube, and you can kind of see that atmospheric pressure is taken as the pressure above the free ambient surface and the free liquid surface within the capillary tube. For hydrostatics to apply, again, we're assuming that all of the surface tension effects are isolated to this meniscus right here. For hydrostatics to apply, we must have a step decrease in pressure across the meniscus when theta is less than 90 degrees in order to satisfy the laws of fluid statics. So for example, we'll have atmospheric pressure above this meniscus, then we travel across this meniscus in thickness, and then right below the meniscus we have a pressure step decrease such that the pressure right below the meniscus is equal to that P infinity, that P atmospheric, minus rho GH, where H is the level above the free ambient surface that the liquid within the capillary tube rises to. Now, right after the meniscus, as we go down further into the capillary tube, hydrostatics applies as it normally does. So as we go in the direction of gravity, the pressure increases with rho GH. So we have P infinity right above the meniscus, then we cross across the meniscus, and then right below the meniscus, we have P infinity minus rho GH. And then as we get down to H, such that we have P infinity minus rho GH plus rho GH, as we have right here, we have atmospheric pressure at the horizontal level at which atmospheric pressure exists. So here at this point in the capillary tube, we have atmospheric pressure. And that has to be the case according to hydrostatics because this point within the capillary tube has the same elevation as this point outside the capillary tube at the free ambient surface, which has a pressure of P infinity. So P infinity exists at this point outside the capillary tube, and P infinity exists at this point inside the capillary tube because they're both at the same elevation. So now at this point, as we mentioned, hydrostatics continues to apply. So as we go a distance delta below this point, we see that we have a pressure of P infinity plus rho g delta, or P infinity plus rho g delta. Well, that's just the pressure as you go a distance delta down from the free ambient surface, such that this is also P infinity plus rho g delta. So you can kind of see that once you cross this meniscus, hydrostatics applies as it normally does. And that's kind of brought home by this graph right here. So you can kind of see that we have pressure versus distance plotted here, and distance is kind of the distance along with gravity, or the distance along negative z. So we can kind of visualize that as we're way above here, way above the capillary tube, and we go down towards the meniscus, our pressure that we're experiencing is really a constant P infinity because we're assuming that there's no appreciable increase in pressure with air because air is so sparse, it's not very dense. So as we go down towards the meniscus in the ambient air, our pressure is relatively constant at P atmospheric. Now, once we hit this meniscus right here, we will experience a step decrease in pressure across the meniscus in the case of theta is less than 90. That step decrease brings us to P infinity minus rho GH. Now, once we hit right below this meniscus, we've crossed the meniscus fully, we've crossed the thickness of the meniscus fully, we are now back to hydrostatics, and our pressure increases with distance again, such that we go from P infinity minus rho GH, and once we go down to distance h, we're back to P infinity, and we go down to distance delta, where P infinity plus rho g delta, and now everything is kind of as we would expect with hydrostatics. So the way to visualize this is the elastic membrane effect of the meniscus is relieving atmospheric pressure on the liquid in the capillary tube. So you can kind of see, if you're looking at this meniscus here, surface tension is pulling up on this meniscus, and that upwards pull on the meniscus is kind of relieving atmospheric pressure on the liquid in the capillary tube, and that's why we see that step decrease in pressure when theta is less than 90. So another way to kind of drive home this point is to look at a free body diagram of just the meniscus, and again we're going to use the simplified assumption that the 2D projected area of this meniscus, so kind of this 2D projected area right here, is the area over which both the hydrostatic and ambient pressures act. And that's just a simplified geometric assumption. We reviewed that in the previous videos. So using that simplified geometric analysis, we could see that our Newton's second law for this free body diagram is PA plus sigma z pi d is equal to P infinity A. So just by looking at Newton's second law for this free body diagram, we can see that P infinity has to be greater than P, or the atmospheric pressure has to be greater than the hydrostatic pressure when the meniscus is shaped like this. So according to our meniscus that we've drawn and our surface tension acting on that meniscus, P infinity has to be greater than P, or P infinity has to be greater than the hydrostatic pressure. And that's how we know, we kind of get an inkling, okay, there probably has to be a decrease in pressure across this meniscus. And to determine what that step decrease in pressure is, we do a hydrostatics analysis on the capillary tube just like this, and then it ends up yielding us a pressure distance curve that looks like this. So the next case we're going to look at is when theta is greater than 90. So let's move on to that right now. So in this case, we have a very similar but somewhat different situation where when theta is greater than 90, such that H is negative and the liquid in the capillary tube retreats below the free ambient surface, there's a step increase in pressure across the meniscus in order to satisfy the laws of fluid statics. And we can see that here we have P infinity above the meniscus, and then we cross the meniscus, and the pressure right below the meniscus is P infinity plus rho g hat, where H hat is just the magnitude of H. So we have that step increase in pressure, and again, once we get to this point right below the meniscus, the standard laws of hydrostatics apply. We have a distance delta here, so we have P infinity plus rho g hat plus rho g delta. So P infinity plus rho g hat plus rho g delta, and you can see that the pressure here in the capillary tube is also the pressure here when we're going down from the free ambient surface, such that this is also P infinity plus rho g hat plus rho g delta. So in this case, you can see it's a very similar situation where once we cross this meniscus, after we have this step increase in pressure when theta is greater than 90, the standard laws of hydrostatics apply. And again, if we look at this free body diagram to the right, we can see why we have that step increase in pressure. So if we draw our meniscus and we use the same simplified geometric assumption where we're looking at the 2D projected area in Z, we see our Newton's second law shows us that PA is equal to P infinity A plus sigma Z pi D, such that the hydrostatic pressure P has to be greater than the ambient pressure P infinity. And just from this free body diagram, again, we kind of get an inkling, okay, so the hydrostatic pressure has to be higher than the ambient pressure, so we must have a step increase in pressure across the meniscus. And then we use a hydrostatics analysis of our capillary tube, in this case, when theta is greater than 90, to determine what that pressure distribution is. So with this pressure distance curve, it's very similar to the pressure distance curve from the previous slide. We have a constant P infinity above the meniscus. As we cross the meniscus, we have this step, this quote-unquote step increase in pressure, where maybe this isn't linear, maybe it's nonlinear of some kind, maybe it's a quadratic, maybe it's logarithmic, etc. But there's some kind of quote-unquote step increase in pressure across the thickness of this meniscus. And then once we get across the meniscus where the pressure is P infinity plus rho g hat, standard hydrostatics applies. And that's why we see this linear increase after the thickness of the meniscus. So a way to visualize this effect when theta is greater than 90 is you can kind of think that the elastic membrane effect of the meniscus adds to atmospheric pressure at the free liquid surface in the capillary tube. So if you look at the capillary tube right here, and you look at the meniscus within that capillary tube, you can see that you have atmospheric pressure bearing down on that meniscus, and surface tension pulls down on this meniscus, kind of making this elastic membrane additive to atmospheric pressure. So you have atmospheric pressure bearing down on the liquid in the capillary tube, and the elastic membrane pushing down on the liquid in the capillary tube. They kind of add together. So again, the elastic membrane effect of the meniscus adds to atmospheric pressure in the case of theta is greater than 90 when the liquid in the capillary tube retreats below the free ambient surface. So at this point, we have a first order pass of what the pressure distribution within the capillary tube actually looks like. Again, if you take a viscous flow class or you take a physical chemistry class that goes into this stuff, you'll see that surface tension is actually quite a bit more complex than we've laid out here. But the view that we've shown in these past couple of videos is quite good and does provide a decent baseline for engineering estimates. So for example, if you're designing a manometer and you're trying to track the free liquid surface within some reservoir such that you can correlate the elevation of that free liquid surface with some pressure in your system, and you're using a photoelectric sensor or something of that kind to track that free liquid surface, you may want to subtract the effects of surface tension to more accurately predict what your pressure is. Now, in that case, Jones' law will probably give you a pretty good estimate. In the other case where, for example, maybe you're trying to do some biological modeling of some suspended particles in a capillary tube, and you need to know what the pressure is at some point along the capillary tube to complete your free body diagram, then a pressure estimate or a pressure model like we've just laid out here is also probably pretty good. Now, if you want to get to hyper-precise, high-resolution estimates, you're going to have to go a little bit deeper than this, but this does provide a pretty good basis from which you can do a lot of stuff. Okay, so that'll probably be it for this video. I really appreciate you watching. Thank you very, very much, and I will see you next time.